I will present today a work that has been done in collaboration with my PhD student, Javier Onam, one member of my group, very important person in this work, Jose Palau, and Luis Correa, my former PhD student, now at the University of Nottingham. I'm coming from Tenerife, Canary Islands, and I have seen everyone advertising the place where they're coming. So the island is in the middle of the Atlantic, in front of Africa, and it has a mountain of 3.7 thousand meters high that gets the snow in winter. And many people have asked me why we cannot go and make a meeting on quantum thermodynamics there. So I'm open to suggestions, and let's see if the next meeting can be in a nice place like that. So let's go to work. So today I will discuss machines that has coherence as an essential feature. It means without coherence they will not work. And I will go out through this outline from motivation just to the result and the conclusions. And what is important in the discussion that we'll make today is that being an essential feature of the machines, that coherence has to be there. If not, the machine will not operate. We'll find out that those machines, the class of systems as we discussed, can be understood in terms of classical thermodynamics. Means I can describe those machines in terms of thermodynamical quantities that can be described in terms of populations without involving coherences. In that sense, the machines are classical. So it's really tempting to link enhancement performance of machines to coherences. And many works are devoted to that. So as soon as we get enhancements in the performance of the machines, we would like to see if coherences are playing a role. And we will show for a certain class of system that this will not be the case. So the questions that we are trying to address are general in a sense that many of us are bothering about them. And it's what is quantum really in quantum thermodynamics. And if we can explore these quantum features I will discuss to enhance the performance of quantum machines. So thermal machines have been the object of study since the pioneering works in the late 50s by Scoville and Jusic. And you will find in the literature many results. Some results are concerning performance, some optimizations of machines. So how to get a better machines in the cooling power, but also in the efficiency of the machine, and also the efficiency of maximum cooling power. And the list, of course, will not be complete. There are many more works devoted to that. Also, there have been efforts to understand truly quantum features in the operations of those machines. And of course, as soon as we have a discrete spectrum, we may say the machine is quantum. But we are not thinking about those quantum attributes as the discrete spectrum of the Hamiltonian, but we are thinking about quantum correlations and coherences are the quantum features we would like to detect on those machines and to see if they are useful to get better performances. So there are very nice words concerning coherences. First, because we know that coherences can be thought as a resource in open quantum systems as they influence the dynamics of those open quantum systems. In other works, have been argued that coherences, especially noise-induced coherences, may enhance the performance of heat engines and also the performance of heat-driven quantum refrigerators. And you will find very useful reviews discussing all those features and many more in the references that I just quoted there. So the field is vast, and it's large, it's getting larger and larger. So we would like to focus in just a little corner of the field. What is not clear is that really in some machines, coherence are just not instrumental. Means they are just there, you need them, but they are not playing any more influential role, because we know from some works that classical incoherent systems can explain the dynamics of those coherent machines. And this is the question I would like to address today. A very nice approach put forward recently by Uzin, Levy, and Kozlov is the following. Suppose you get a coherent machine, and then you add some dephasing. And at the end of the day, you see that the efficiency of the machine has been reduced. Then you may take that's an indication that really coherence is very important in the machine, because adding noise is just getting a worse machine. Also, there are some experimental proposals on that idea, thinking that if at the end you can just figure out what is the ultimate bound of the performance of incoherent machines, as soon as you get violations of those bounds, you are implying what coherences are playing in those devices. Also important reference, I think, is Kluwer and Segal, and I recommended you to go there. So in this talk, I would say that the machine is truly quantum if its thermodynamic behavior cannot be replicated exactly by an incoherent emulator. That's the definition I'm adopting here. So as soon as I get a machine in which I can write a classical emulator, I will not think of that machine as a quantum machine, truly speaking. And we will show that many coherent thermal machines are thermodynamically speaking indistinguishable from the classical emulators, meaning that if I only have access from outside to the energy conversion processes and the efficiency of the machine, I will not be able to distinguish one from another. The class of system I will introduce here to set up this question is the following: a cyclic n-level system in which we have many, many transitions. Some of them are connected to a hot bath at higher temperature, that a cold bath that is connected to all the transitions, and one single transition is driven by an external classical field. So this is a machine that is driven. And we will study that machine in the weak driving limit. That's the game I'm going to play. And of course, coherence is essential for the machine to operate. That transition has to be promoted. If not, machine will not work. However, I will show that the steady state operation of that machine admits a classical description based on graph theory, means it can be described by a population dynamics equation. For simplicity, instead of getting the n-level machine, the results in our preprint are for n-level machines, but I will just fix here 3 and 4 level systems to be pedagogical, say. So I will study a 3-level refrigerator that suggests I study also a 4-level model, a hybrid refrigerator in which is partially driven by an external acid seal, but also partially driven by a heat bath. And we will show that the 4-level model has a wider cooling window, larger cooling power, a larger coefficient of performance. In addition, both models show that the energy conversion rate is exactly proportional to the amount of coherence you get in the stationary state. And as a result, we will show that the better performance of the 4-level system matches exactly the extra amount of coherence you get in the stationary state with respect to the 3-level machine. So from those facts, we may say, okay, coherence are playing a very important role because as soon as I get an extra coherence, I get a better machine with respect to the 3-level machine, speaking about the 4th. The level configuration of the machine, the 3-level, is simple, and the only thing to take care here is that we add an extra level between the 3 and the 2, meaning that it's partially driven by external field, but also by the heat bath. Somehow we are recycling part of the energy that's going to the hot bath to make the machine operates. So the math that we will put in that system is the following. We'll consider a bare Hamiltonian that is just the spectrum of the n-level system. There's an external driving field that we'll call HD, that it has the basic harmonic configuration in time that we know. We will use the resonant coupling in the level that will be, the transition will be excited, just for simplicity. And as usual, we will connect our model. The bath has 3 bosonic modes with certain rates that are written there. So it's the classical setup. Because we want to discuss the weak driving limit, we will have to take care of the time scales involved and be very careful when we are dealing with the equation to know that it's precisely a very good approximation. It's not violating any principle of the thermodynamics. So there's one time scale associated with the bath, and it's just the inverse of the temperature for the cold bath. The bare Hamiltonian means the system also has some natural time scales deriving from the frequencies of the transitions. Let's call it T0. There is a relaxation time scale associated to the rates and the connections of the central system to the environments. And also there is a time scale associated with the driving. We will work in the weak driving limit, means that we will consider the following difference in time scales. And we have to be very, very careful in respecting that in the derivation and also in the simulations. If you do all the computations and you go to the rotating frame and neglect the fast rotating terms, you will reach a local master equation of these forms that is the starting point of our discussion. We have checked that with the exact description in say, considering all the couplings, and it works fine, that approximation. So, as I said, from that set of equations, we can derive the energy fluxes present in the model and also the power, and they can be computed from the bare Hamiltonian and the dissipators of the master equation I just wrote before. And if you go to the stationary state, a careful analysis done by people like Spohan and Maliki show that we are not out of any principle of thermodynamics. We have the first and the second law perfectly satisfied. So the model is consistent in this weak driving limit with those laws. So let's go to the first system, the three-level system. So I can get the stationary state, and I can get the energy currents and the power. And what is important is all the energy conversion processes are proportional to the same current. That is proportional to the amount of coherence in the stationary state that you get. So everything is coherence in this model. And because the rates are just proportional to the same current, we know that the machine is Ender reversible, so it's able to reach the maximum efficiency. And the efficiency of this machine is just the ratio between the frequency associated to the cold transition respect to the driving. If we go to the fourth level model, we will get similar equations as presented before. So we get an extra cooling window, so it's a larger cooling window. But again, the machine is endo-reversible, and again, the energy conversion process is proportional to the amount of stationary coherence we have in the machine. So simple for that moment. But if we want to compare one machine to the other, let's take one indicator. First, I will look at the cooling rate, and I will consider the amount of cooling rate of the four-level model respect to the amount of cooling rate respect of the three-level model. And I know exactly that this ratio is the ratio between the amount of stationary coherence in the stationary state the machines get when they reach the infinite time limit. If I get that bigger than 1, it's an indication that this machine is getting extra coherence with respect to this one. We are setting the same parameters for coupling to the environments, etc. We are not changing, just adding an extra level. So fixing those parameters and being consistent with the weak coupling assumption, let's just show one of the pictures. Let's fix our attention to the full line here. So this is the ratio between the cooling rate of the four-level machine with respect to the three-level machine. And for this thermodynamic force smaller than 0, mean negative value, you see that you get bigger than 1 ratio. So an extra amount of coherence in the four-level machine. But if you look at the ratio of the coefficient of performance of the four-level machine and the three-level machine, you see that there is also in that range of parameter that you get a better efficiency of the machine. So in this range of parameters, what do you have is that the machine gets a larger cooling power, also a larger efficiency, I have not shown here, but also larger cooling window. So it seems that the four-level machines is working better than the three-level machines, and everything is due to the fact that you are getting extra coherence in that machine with respect to the three-level machine. However, both machines can be described classical, and this is why we'll show you the simple example of the three-level machine. So that will be the set of equations, including populations and coherences of the three-level machine, just as sketched there. And if you look at the stationary state, you will see immediately that you will be able to make a graph representation of these equations. So each vertex will be one of the levels. Blue line indicates connections to the cold bath. Red line indicates connection with the hot bath. And the green line is the connection with the external laser field. And if you look carefully to those quantities, you should be able to write the rate equation precisely from those coefficients. That is a faithful rate equation, so it verifies all the properties you should have. So I may define a system that is ruled by this rate matrix that is completely classical, and it has the same stationary state as the coherent machine. You will be able to show with the tools that you get from graph theory the cooling power of that machine just directly from this transition matrix. So you define some algebraic coefficients with the cooling rates, getting support on the following. So you have the 3 levels. You have the transition rates between those levels, and you define a cycle that is, let's say, C. That is the one that is going from 1 to 2, from 2 to 3, and to 3 to 1. And you associate an algebraic number to that cycle that is just the product of the transition matrix elements. You also have an inverse cycle that is depicted here, and you associate also an algebraic number that is just the product of transition rates. Also, you define the same numbers, but just restricted to the bones that are connected to the cold and the heat bath. So from this, you select 2, 1, and from this, that is the hot, you select 1, 3, or 3, 1. just from that information, you just get the thermodynamic forces for the cold and hot bath of this model. That is just the Boltzmann constant times the log of the ratio of those quantities restricted to COH, meaning hot and cold bath. That's a simple construction, and then you get explicitly the current for that model. The important point here is first to see that not only the force has to be high if you want to get a better cooling power, but also the asymmetry contribution of those cycles. Larger is this different, higher cooling power do you get. And this suggests the 4-level model. And second, this coefficient here in this model grows like the number of levels squared, meaning that if you want to get a better machine starting from the 3 level, the best option is 4 levels, because as soon as you get higher number of levels, that number is increasing. Like as n squared, you will get a reduction of that number. So in doing so, you will be able to compute, as I said, that cooling power, and matches exactly, of course, the cooling power of the 3-level machine. So in a way, the machine, even if coherence is essential to the operation of the machine, if I'm outside and I'm just measuring heat currents and efficiency of that machine, means thermodynamically speaking, I'm able to write just a transition matrix rates, get my computation, and model perfectly the stationary operation of that machine. In that way, I say it's classical machine. If you want to know that it's fully ruled by coherence, you will have to look at the internal structure of the machine and deploy there all your tools to put in evidence that coherence is there operating. So the statement, following the consideration I have made here for you, is that this class of systems can all be emulated classically, so coherence are not really necessary to explain the thermodynamic behavior of those machines. So the questions will be next, if there are some coherence machines that cannot be emulated classically. It means that if I just measure the thermodynamical quantities on them, then just a model that is classical in population will not be sufficient to explain what I observe. I would like to thank all my collaborators in these works, not only this one, all what I have been learning on this quantum thermodynamics, that is Jose Palau, Luis Correa, Gerardo that is here, and Javier Onam. And also I would like to thank the Spanish government for the little amount of money that is giving us to spend. Thank you very much for your attention.
Okay, so we have quite a bit of time for questions.